we'll get going. Okay, on your dog, go ahead.
Okay, so this question is about the lab that is due today.
Which one is that?
It's the mass spectrometry thing.
Okay, go ahead.
So you know how you have procedure, data, and results all in the same thing together?
Right.
So I didn't know that you wanted like the answers like right after the steps. So I wrote out all the procedures and I was writing out the data on a step on the page on different set of pages.
Yeah, see, that's not a good lab technique on your dog. You're supposed to, the whole point of the lab was to put yourself out there and make guesses as to what the answer may be.
Well, I was going to each of them and I left 2 gaps of pages so like to put the data on.
Right, but the whole point of the lab was to put you out of your comfort zone, not try to make the lab look neat, but try to make it look like you're trying to figure stuff out as you go along. Are you with me here or not?
Yeah, I realized that on the second step. So how do you want me to do it now?
Well, there's not much you can do. Just turn in what you have. I mean,
Okay,
you can't like undo the lab once you've done it. You know what I mean?
yeah, so there's gonna be deduction, right?
Probably, yeah. You live and learn.
All right, okay.
Okay.
All right, thank you.
All right, Madison, any questions? And is it Madison or Madison? Madison?
Oh, it's Madison.
So it's kind of like Madison, but with a Y.
Yeah.
Okay.
And
You
no
know-
question.
You know about that name, Madison, right?
What name?
Madison.
Yeah.
It never used to be a name.
Well,
It's only
Nope.
been a name for about 25 years.
okay.
Do you know how it came about?
Mm-mm.
Do you know who Tom Hanks is?
Yes.
Do you know that movie Mermaids?
No.
So there's a movie with him where he finds a mermaid, right?
Mm-hmm.
And she falls in love with him. And they're walking around town and they're trying to figure out a name for her. And she says, when she sees a street sign, she says, Madison. And he said, that's not a name. So her name ended up being Madison. And Madison became one of the most popular girls' names in the United States.
Yeah, it is pretty popular.
Yeah. I have a niece named Madison. But I just think it's kind of neat that that did not used to be a name fairly recently. All right. So on your dog, you still have your hand up. You got another question?
I just forgot to take it down.
Okay. Which, did your arm get tired?
No.
Okay. I'm going to change my share, people, so that we can look at some things that you will need to know for the test. They may or may not be on there, but they're fair game. Okay. So if you can see this question, give me a thumbs up or something like that. Okay. Excellent. So you can see that this question talks about an Alka-Seltzer tablet, 324 milligrams of aspirin, some sodium bicarbonate, and some citric acid. It says calculate the moles of each substance in the tablet. So what I'm going to do is I'm going to do it for aspirin because there's a follow-up question about aspirin. I'm not going to do it for all three of these because the way I do it for aspirin is the way you do it for all of them. So moles of aspirin. So the first thing you're going to do is you're going to calculate the molar mass of aspirin. So there are 9 carbons. Well, I'm just going to do this. There's carbon, hydrogen, and oxygen. 9 carbons, 8 hydrogens, and 4 oxygens. Looking at the periodic table, each carbon is 12.01, each hydrogen is 1.01, and each oxygen is 16.00, which comes out to 108.09, 8.08, and 64. When we add these all together, we get 17 here, we get 0 here, carry the 2, we get 180.17. So what this number means is are two things. That one aspirin, and I'm going to abbreviate aspirin as ASP, is equal to 180.17 atomic mass units, or 1 mole of aspirin is 180.17 grams. So that's what this number means, two separate things. Okay, now that we have, and this second one is called the molar mass, the gram mass of 1 mole, we can take our 324 milligrams of aspirin, turn that into grams of aspirin, and turn that into moles of aspirin. So one way to do it is this way: 324 milligrams of aspirin times 1 gram of aspirin over 1,000 milligrams of aspirin, and then times 1 mole of aspirin over 180.17 grams of aspirin. So this is one way to do it. And when you do this work, what is the answer? This will go into this almost 2 times. So it's going to be 2 times 10 to the minus 3 as kind of an estimate. This doesn't go in really 2 times. So maybe 1.7 times 10 to the minus 3. We're allowed 3 significant figures because of this. And I get 1.80 times 10 to the minus 3 moles of aspirin. And we did a calculation this morning and this afternoon. Well, I'll leave that for the second part. Another way to do this is to do this. Now, we know that the milli means a particular thing. And that particular thing is, it means 10 to the minus 3. So I could start with this. And then multiply by this conversion, and I get the same answer as above. So if you showed me this for this problem, that would be full credit. If you showed me this for this problem, that would be full credit. Any questions about the solution to A, where we're supposed to find moles of aspirin? Okay, there being none, let's go to B. B, we're supposed to find out molecules of aspirin. And since we've already have the moles of aspirin, we might as well start there. So here, I could put 6.022 times 10 to the 23 aspirin molecules, but I'm not going to write molecules there because I have the word mole here, and we might confuse those. So when you multiply these two values together, you're going to get about 10 to the 20 and 10. So 10 times 10 to the 20, or 1 times 10 to the 21. And let's see what we get. And we get 1.08 times 10 to the 21 aspirin molecules. So this is the kind of work I'd expect to see for the second part. Are we good to go on this? Okay. Now, this morning, we did a little calculation where we took 101.08 times 10 to the 21 aspirin and divided that by 37.2 times 10 to the 12. cells. So 10 to the 12 is a trillion. On Google, they said that there are about 37.2 times 10 to the 12 cells in the human body. So if we divide one by the other, we get 2.91 times 10 to the 7th aspirin per cell. So if you were to take this tablet that has 324 milligrams of aspirin, you'd be getting about 30 million aspirin molecules per cell. 30 million. Now, there are these things called baby aspirin, which are about 1/4 the size of this. So 1/4 the size of this would be 7.5 million aspirin molecules per cell. 7.5 million for baby aspirin. So I want you to think about that. Tiny little baby aspirin, 7 million molecules per cell. Does that sound impressive? Sounds impressive to me. Makes you wonder why you need to take 80 milligrams. All right. So when you do take these pills and stuff, you are getting millions of molecules per cell, just so that you know. All right, let's move on. So does everyone understand how to calculate molar mass? Yes or no? Yes? Okay, so for you, Izzy, here was the calculation of the molar mass. Number of atoms times the mass of one atom, add them all up together. And now do you understand how to turn this into moles of a particular molecule? Yeah.
Yeah, I'm
That's
pretty
right.
familiar with it.
And then here, this is how you calculate how many aspirin molecules.
Mhm.
So, okay, let's look at the next one. Now, this one enables me to show you how to use percentages correctly instead of how you were probably taught in math. So calculate the mass percent of titanium in the mineral ilmenite, which has the formula FeTiO3. What mass of ilmenite is required if you wish to obtain 750 grams of titanium? So mass percent is equal to the mass of the part over the mass of the whole times 100%. That's the definition of formula for mass percent. So in this case, if we want the mass percent of titanium in ilmenite, our words would look like this. The mass of titanium in ilmenite over the mass of ilmenite times 100%. So what are we going to use for the mass of titanium and what are we going to use for the mass of ilmenite? Well, I'm going to use the mass of one titanium atom. And one titanium atom to 4 significant figures is 47.87 U. So what is the mass of one ilmenite? Well, 55.85 for a iron, 47.87 for a titanium, and for 3 oxygens, it's 48.00. And I'm putting the U outside the brackets so I don't have to write it for every one of these, and then times 100%. So when you add these numbers on the bottom together, you get 7 plus 5 is 12, carry the 1, you get 7, carry the 1, you get 12, 13, 1, carry the 2, and you get 15, 151.72. And since this is good to the 100th, this is good to the 100th, and this is good to the 100th, this is good to the 100th. So now I've got 4 zig figs divided by 5 zig figs times infinity zig figs. So I should get 4 zig figs. and you get 31.55%. So what does this 31.55% mean? It means that you have 31.55 grams of titanium for every 100 grams of ilmenite. So that's what this means. Any questions about that? Now, some people look at this, and a lot of math instructors taught you, okay, so think of that as 0.3155. And this really means 0.3155 grams of titanium for every 1 gram of ilmenite. But this is kind of silly to use because percentage is not based on 1, it's based on 100. So don't move the decimal over. Okay, now the second part says, well, how many grams of ilmenite would you need if you wanted 750 grams of titanium? So I'm going to take my 750 grams of titanium and I want to figure out the grams of ilmenite. And I'm going to use this right here. So one side goes in the bottom and the other on the top. And I think it's fair to say that the 31.55 goes on the bottom so that the titanium cancels. Therefore, the 100 grams of ilmenite goes on top, and we would be able to calculate how many grams you would need of ilmenite to get 750 grams of titanium. You can tell that this is about 3. This will go into that about 3 times. 3 times that should be around 2,250. And let's see what we get. 750 times 100 divided by 31.55. Here we only get 2 significant figures. So we get 2.4 times 10 to the 3 grams of iron titanium oxide. So this is the kind of work I would expect for the second part. This is the kind of work I would expect for the first part. And that's how you use mass percent. Now imagine if you would just move the decimal over 2 places. Half of the students in our class would have done this. And they would have got an answer of about 250, which would be wrong. It needs to be divided by 0.3155. So writing these out with units and labels is so much better than just moving the decimal over. So I know it's frightening at first to use percentage the way it's defined, but that's what I want you to do. Any questions there? So let's do a little practice here. Let's see. Let's say that you dig up some ore and it's 42.5% copper. What does that mean? So 42.5% copper in copper ore. Write out what that means. When you're done, give me a little thumbs up, like I'm done. How are you doing, Madison and Stephanie? You got it, Stephanie? How about you, Madison? So there are 2 ways to do this. One is this, 42.5 grams of copper over 100 grams of ore, or you could say 42.5 grams of copper is equal to 100 grams of ore. Either way. but percentage goes with 100. Don't move the decimal over. Any questions? Okay, we're going to put that off to the side. We're going to do the next problem. Okay. An organic compound has the empirical formula of C2H4NO. If its molar mass is 116.1 grams per mole, what is the molecular formula of the compound? So, to get the molecular formula of the compound, you take the empirical formula and you multiply it by some multiplier. To get the multiplier, you take the molar mass of the molecular formula divided by the molar mass of the empirical formula. Whoops, that's supposed to be an F. Now, the empirical formula is C2H4NO. Let's get the molar mass of the empirical formula. So we've got carbon, hydrogen, nitrogen, and oxygen. 2 carbons is 24.02. 4 hydrogens is 4.04. 1 nitrogen is 14.01. And 1 oxygen is 16.00. Add these all up together and you get 07 and 34.58. So that's the molar mass of the empirical formula. So this becomes 116.1 grams per mole over 58.07 grams per mole. And it doesn't take a lot to see that this is going to go into there 2 times. So that's our multiplier. So the molecular formula is going to equal C2H4NO, but we need 2 of them. So C4H8N2O2. So it's 2 times 2, 2 times 4, 2 times 1, 2 times 1. And that's how you get the molecular formula. Any questions there about getting the molecular formula of the compound? Now, what is the difference between the molecular formula and the empirical formula? The empirical formula cannot be simplified. So if you look at the subscripts, one of them, I should say, you can't simplify them because they don't have a common factor. What do these subscripts all have in common? You can divide 2 into them. So that makes this the molecular formula. So they call this the molecular formula because that's the molecule's formula. They call this the empirical formula because you would find this empirically through experimentation. Okay, next problem. So complete the following table. We want to find the molecular formula. If the molar mass of the molecular formula is 150, find out the molecular formula. So remember for this one, the molecular formula is the empirical formula with some multiplier. And to find the multiplier, you take the molar mass of the molecular formula divided by the molar mass of the empirical formula. So in this case, you got 150 grams per mole. And for this guy, 2 carbons is 24, plus 3 is 27 for the hydrogens. And then 27 plus 48 is 27 plus 48 is 75. Now, you'll notice I didn't do a lot of detail on this one. I just said, hey, it's around 75. Notice how many times 75 goes into 150. It's 2. So that's our multiplier. That means our molecular formulas, and you don't need to do the multiplying. You don't have to write it out. You can just say, hey, if the multiplier is 2, then it's C4H6O6. Now, it does look better if you do this. All right. So I'm going to stop here for a moment and point out to you that your multiplier should always be close to a whole number. You know, it might end up being 1.9 or 2.1 or 2. But if you get a multiplier that's 1.5, something's not quite right. Okay, with that being done, I want you to do B and give me a thumbs up or a yes when you're done. Okay, we're going to go ahead and do it. So the molar mass of the molecular formula is 44.1 grams per mole. 3 carbons is 36. 8 hydrogens is 8. 36 plus 8 is 44. So we get our multiplier is 1. When your multiplier is 1, that means the molecular formula equals the empirical formula, which in this case is C3H8. Sometimes your molecular formula and empirical formula are the same. So let's do this one here. Here's the molecular formula. Here's the molar mass, and what's the empirical formula? Now remember, the empirical formula is the simplest ratio. So let's do that first. What's the empirical formula for B4H10? When you've got it, give me a thumbs up. What's the empirical? So can these subscripts be divided by something? Is there a common factor when you have a 4 and a 10?
B2H5.
Yeah, B2H5. Because 2 will go into that 2 times, 2 will go into that 5 times. So what's the empirical formula of this guy roughly? Well, each boron is roughly 10. What is it? 10.8. So 10.8 times 4 is 43.6. And 10 hydrogens is 10, roughly. So it's roughly 53.6. So any questions about that one? That one wasn't so bad. We're going to see one I think that's a little more interesting here. This morning I was talking about this one here, nicotine, a poisonous compound found in tobacco leaves. is 74.0% carbon, 8.65% hydrogen, and 13.35% nitrogen. Its molar mass is 162 grams per mole. What are the empirical and molecular formulas of nicotine? Now, if that nicotine wasn't so bad for you, it actually sounds kind of like a cool name, right? What's your kid's name? Oh, his name is Nicotine. We call him Nico for short. Okay, so the way you do this is you take the percentage, you assume you have that many grams, you get the moles, and then with the moles, you get the formula. So that's the step, percentage to grams to moles to formula. So we're going to assume that we have exactly 100 grams of nicotine. If you had 100 grams of nicotine, that would mean you have 74.0 grams of carbon. And you have 8.65 grams of hydrogen. And you have 17.35 grams of nitrogen. So this is assuming that you have 100 grams. Now I'm going to take the grams of carbon and turn that into moles of carbon. So 74.0 grams of carbon times 1 mole of carbon per 12.01 grams of carbon. You can see this is going to go in about 6 times. Let's find out what we get. 74 divided by 12.01, and I get 6.162 mole of carbon. Here, I'm going to do 1 mole of hydrogen per 1.01 grams of hydrogen. And I better get pretty close to 8.65, agreed? And I get 8.56, which I think is pretty close. Whoops, that's mole of hydrogen. And then here we're going to do 1 mole of nitrogen per 14.01 grams of nitrogen. And we get 1.238 mole of nitrogen. So that's how many moles of each of these. Now, this is the way I like to do the next part. I don't know that the book does it this way, but this is the way I do it. I say C 6.162, H 8.56, and nitrogen 1.238. So that's the formula. But we don't like formulas that aren't whole numbers, so we need to turn these into whole numbers. So the first thing I do is I divide by the smallest of these. That way, the smallest one becomes 1 and the other ones become greater than 1. The reason I divide by the smallest is because I don't want a subscript to be lower than 1. And if I divide by the largest, 2 of these become lower than 1. I don't like that. So when I do the work here, and I do the 6.162 divided by 1.238, rounding off to the correct number of sig figs, I get 4.98. And for hydrogen, I get 6.91, and for nitrogen, I get 1. So here's the thing that you want to struggle with just a little bit is, are these numbers close enough to whole numbers to call them the way they are? So is this close enough to say it's C5H7N? And that's the empirical formula. Is it close enough? Well, let's check and see. So if that's the empirical formula, to find out the molecular formula, I'm going to get the multiplier. The multiplier is going to be the molar mass of the molecular formula over the molar mass of the empirical formula. We're given 162 grams per mole for the molecular formula. And we need to figure out the molar mass of this guy. Oh, there we go. So what is the molar mass of this guy? Well, every carbon is 12. 5 times 12 is 60. Hydrogens are 1, so that's 67. Nitrogens are 14, so 67 plus 14 is 81. And I think you can see that that's going to be a 2. And we're happy that our multiplier is a whole number. So that means that the molecular formula is going to be C5H7N times 2, which is C10H14N2. And so that would be the molecular formula. Any questions there? So I should say we're kind of happy that this happened to have a molar mass that was precisely half of that, and we got a whole number multiplier. So we're pretty certain that that's the empirical formula. Okay, so let's do another one. Let's see. So this is a very interesting problem because it's just like the others, only slightly different. So I'm going to give you a moment to read this. Okay, so let me show you what we're doing here is we're saying sulfur, which is a solid, combines with fluorine, which is a gas, to give us SFX, which is a gas. I know this is a solid because most elements are solid at room temp. The only two liquids are bromine and mercury. The gases are the noble gases plus some other nonmetals. F2 is one of those nonmetals, that's a gas. And I know this is a gas because, well, it says so. I know that there's 1.256 grams of sulfur, and I know I get 5.722 grams of SFX. Now, here, because of the law of the conservation of matter, whatever this number is, this plus this should equal that. So if I do 5.722 and subtract from that 1.256, we get 6, 6, 4, 4. We get 4.466 grams of F2. Now, this is not the way to do the problem, but we could do this, that the percent sulfur is 1.256 grams over 5.722 grams times 100%. And we get 20 something percent. Let me find out, 1.256 divided by 5.722. We get 21.95% sulfur, which means the percent fluorine is 78.05% because these two numbers should add up to 100. So I could do this problem the same way I did the previous problem and start off with the percentages, that many grams and so forth and so on, but we're not going to do this. Because normally when you do a problem like this, you actually start with masses. So instead of going percentage to grams to moles to formula, we're going to cut out the percentage and we're going to go straight from grams to moles to formula. So we have 1.256 grams of sulfur and we have 4.466 grams of fluorine, Notice I put F here and not F2, even though this is underneath the F2. I want you to go ahead and calculate moles of sulfur and moles of fluorine and see if you can get the formula. Give me a thumbs up when you're done or a check. Okay, so let's start plugging numbers in. 1 mole of sulfur to 32.07 grams of sulfur. 1 mole of fluorine to 19.00 grams of fluorine. So here you're going to get a number that's far less than 1. So I get 0.03916 mole of sulfur. And this ends up being 0.2351 mole of fluorine. So you get S 0.3916 and F 0.2351. I'm going to divide them both by 0.03916. And I'm going to get sulfur 1 and fluorine 6. And there it is. So you see, you need to show this work. You need to show this work so that you show how you calculated the mass of fluorine, and you're good to go. This stuff you don't need to show. This is to help you see that that would be 4.466. Now, let me show you something else. This is 4.466 grams of F2, and it's not 4.466 grams of F. So let's actually use the formula F2. And since there's 2 fluorines, the molar mass is twice that. Now, to figure out the formula over here, I don't want moles of F2, I want moles of F. So if you take a look at F2, I actually have 2 fluorines for every 1 F. And this is the equation I could be using instead of the one above. Well, what answer am I going to get here? And the answer is the same as the one above. Because you have 2 divided by 38 is 19 on the bottom, which is what we have there. So when you're trying to figure out the number of that particular element, it doesn't matter whether it's F2 or F. So you might as well just start with F instead of F2, okay? Are we good to go?
Oh, wait. Oh.
Go ahead. Pull your
Hold on.
copy down.
Just the last portion. Okay.
This part
Yeah.
you need now. Remember, we start with F, not F2, because it's easier to do that.
Oh, yeah.
Yeah, see, this gives us the same answer. So why bother with this step? Most people, they forget that. So don't start with F2, start with F. Okay?
Okay.
Okay. Now, for this problem, I don't usually ask a question like this on the exam, but I do want to explain to you what this term allotropes means. So allotrope simply means two different forms of the same element. So allotropes of carbon are as follows. The most commonly known ones for carbon are diamond and graphite. The two most common known forms of carbon. For oxygen, there's O2 and O3. Gaseous oxygen and ozone. For phosphorus, there's red phosphorus and there's white phosphorus. Can you guess what color red phosphorus is? It's red. How about white? It's white. And these different allotropes behave differently under chemical conditions. You can burn graphite, but you can't burn diamonds. From commercials 30 years ago, diamonds are a girl's best friend, but graphite is not. Ozone protects the earth from ultraviolet light. Oxygen doesn't. Ozone would, if you subjected yourself to it regularly, it would kill you, whereas oxygen doesn't really do that. All right, so do you understand allotropes? Different forms of the same element, not isotopes, allotropes. Okay, any questions about that one? No? Okay, we're gonna go on. So this is another one that we're gonna do quickly. The recommended daily allowance for women 19 to 30 years old is 18 milligrams, and this is iron. How many moles of this? So you already know I would start with 18 milligrams of iron and turn that into 18 times 10 to the minus 3 grams of iron, because milli means 10 to the minus 3. Then to get moles, I would multiply by 55.85 grams of iron per 1 mole of iron. And where do we get that 55.85? Well, for iron, it is right here. And so we can estimate this answer. 18 is 20, 55 is 50, 20 times 50 is 1,000. So we get 1,000 times 10 to the minus 3. So we should get around 1 gram, I think. 18, clear. 18 second EE negative 3 times 55.85. And holy schmoly, we get 1.0 grams of iron. How's that for estimating? So any questions about how many moles? Now, to get how many atoms, we would take our 1.0 grams of iron and multiply by 6.022 times 10 to the 23rd irons, and that would be iron atoms, per 1 mole of iron. And you can see that this answer is going to be 6.0 times 10 to the 23 iron. And that means iron atoms. So any questions on how to get moles or how to get atoms? Okay, then we're going to move on.
Hey, I have one for you. On that last one, wasn't the equation upside down? You had, shouldn't the, no,
this
no,
one.
yeah, shouldn't that, you have the molds in the wrong place.
Yes, you're right. So we got to cross that out. Do it again.
Yeah, well, yeah, you got it backwards.
So 1.8 times 10 to the minus 3 grams of iron times 1 mole of iron per 55.85 grams of iron. Good thing you said something there, Greg. So now we can fix it. And this is a harder one to estimate, but one thing we can say for darn sure is that my light is too bright. There. One thing we can say for darn sure is that the answer better come out to be smaller than 1, right? So 3.2 times 10 to the minus 5 mole of iron. And then for the atoms, we do 3.2 times 10 to the minus 5 mole of iron times 6.022 times 10 to the 23 iron per 1 mole of iron. And this should come out to be about 20 times 10 to the 18 or 2 times 10 to the 19. And I get 1.9 times 10 to the 19. Okay, good catch, Greg. Everyone, you should do a little clap for Greg. A little clap emoji thing. Okay, and Greg, if you look at the participant list, you're going to see the one where you pat yourself on the back. You should find that one. Okay, there is no pat yourself on the back, but you deserve a pat on the back. Okay, this is a great question for a multiple choice question on a quiz. Which of the following samples has the largest number of ions? So if we look at each of these, this has 1 beryllium ion and 2 chloride ions for 3 ions, okay? This also has 3 ions, 1 magnesium, 2 chlorides. This has 2 ions. This has 2 ions, 1 strontium, 1 carbonate. And this has 2 ions, 1 barium and 1 sulfate. Now, if we were looking at a mole of this, we would actually say that it has 3 mole of ions for every 1 mole of that. So it's really important to be able to look at these things and tell how many ions you have. So if I had 1 mole of that, 3 mole of ions, 1 mole of that, 3 mole of ions. So what am I going to do with that number? I'm going to start with 1 grams of each of these and get the molar mass of each of these and figure out what's what. So the molar mass of beryllium chloride, I know that Cl2 is about 71. I know that carbonate is about 60. I know that SO4 is 96 and sulfur is 32. Beryllium is, I want to say 9, close enough. Magnesium is 24.4. Calcium is 40. Strontium, I don't know. 77? Nope, 87.6. And barium is 137 point something. Okay. So the molar mass of this guy is going to be 71 plus 9 or 80. The molar mass of this guy is going to be 24.4 plus 71, which would be 95.4. The molar mass of calcium and a sulfur is going to be around 72. The molar mass of a strontium and a carbonate is going to be 87.6 plus 60, 147.6. And barium sulfate is going to be 137.3 plus 96, which is a big number. 200 and, oh gosh, 43, 33. Okay, so if we have 1.0 gram of beryllium chloride and multiply by 1 mole of beryllium chloride for every 80 grams of beryllium chloride, and then multiply by 3 mole of ions per every 1 mole of beryllium chloride, we would get some sort of number over here, correct? I don't know what it is. If we do this for the next one, we get these numbers here. Now, do I need a calculator to figure out which calculation is going to get me a bigger value? And I don't think so. I think here, since this is a 1 and this is a 1, and this is a 3 and this is a 3, that's a push. I think the bigger one is going to depend on this 95.4 and this 80. And since this is a smaller number that you're dividing into stuff, and this is a bigger number, this is going to be bigger, and this is going to be smaller. What do you think? And we can do the same for all of these. For all the rest of these, it's going to be times 2 mole of ions. And not 3. So that's going to make the answer about 50% smaller. And to boot, most of these molar masses are bigger. This is the only one that's kind of close. And if you look at that calculation to that calculation, I can tell you right away that this number will be larger, because this number is only 10% smaller than that, but this number is 150% bigger than that. So that's going to win out. So for a multiple choice problem, you wouldn't really have to do all these calculations. You just say, oh, that one. Why? Because it's got a small molar mass and it's got a whole lot of ions. Okay, so that's that problem. This one is more of a conceptual problem. Not too many calculations. We can do some calculations down here. But let's take a look at what are the names of BAF2, SiCl2, and NiBr2. This one is going to be ionic because it's got a metal in it. This one's going to be ionic because it's got a metal in it. So we're going to use ionic names. This one, there's no metals in it, so it's going to be a molecular name. Let's start off with the molecular name. It's easier. Silicon tetrachloride. Now for the ionic name, these are the ions. This one is in group 2A, so we don't need to tell people the charge. It's got to be a charge of 2. Has to be. So we call this one barium fluoride. This one has got 3 ions in it. And we know that nickel is in the middle of the periodic table, so we don't know what its charge is automatically. Bromines are -1, so that means the nickel has to be +2. And because this is not in group 1A, 2A, 3A, it's not silver, it's not zinc, we have to tell people its charge. So nickel 2 and bromide. In answering A, how to name each of these, we've also answered B, which ones are ionic and which ones are molecular. Ionic, molecular, ionic. Now for C, which has the larger mass, 0.5 of this, 0.5 of this, or 0.5 of this? Well, a barium fluoride is going to be 137 plus 38, which is 175. And SiCl4 is going to be 142 plus 32, 142 plus 174. And a NiBr2 is going to be 80 plus 80 plus 50. We're going to just call it 59. So 80 plus 80 is 160 plus 59 is 180 plus 59, 60, 240, 239. That can't be right. $219. Okay, so we have 0.5 mole of BAF2 times 175 grams of BAF2 to 1 mole of BAF2. This is going to be 0.5 times 174. This is going to be 0.5 times 219. And the question is, which has the larger mass? Well, can you see that? This one's going to have the larger mass because you got 219 versus 174 versus 175. So there's your larger mass. So this is a great multiple choice type question too, where you don't actually have to do the calculation to find out which one's the largest. Any questions about that? Okay. Wow, it's already 7. This is another one of those empirical formula ones where you're given percentages. So remember, you start off with 22.88 grams, 5.76 grams, and 71.36 grams, and you go from there. I want to spend the last bit of time doing this problem here because you're going to do a lab like this tomorrow. Okay. So there are these solid compounds called hydrates that have molecules of H2O associated with them. I hesitate to call them molecules of water because water is a liquid and this stuff is a solid. And it's not like a pasty solid, it's a solid. So I'm going to say that it has molecules of H2O associated with it that are still part of the solid. Okay, so if you take this alum, potassium aluminum sulfate, hydrate, and you heat it up, what's going to happen is you're going to get potassium aluminum sulfate with no hydrate. And to account for the hydrate, we're going to put HX2O. So when you heat this up, this is a solid, this is a solid, and this is a gas. We call it steam. So when you heat this up, this steams away. Okay, it evaporates. If we start off with 4.74 grams of this stuff, and we sit around and weigh what is left over, we will get 2.58 grams of this stuff. Now, you can't really weigh the water that escapes unless you trap it. So let's pretend we did not trap the water. How would we get the mass of H2O here? And the answer is that this mass should equal this mass plus the mass of H2O. So to get the mass of H2O, we take 4.74 and minus 2.58, and we'll get 2.16 grams. So that's how you would actually get this number here of 2.16. Now, our job is to figure out what this X value is. The way to do this is you take your potassium aluminum sulfate, your 2.58 grams, and you multiply by 1 mole of potassium aluminum sulfate. And this guy has a molar mass of 96 plus 96. I don't want to show you how to calculate molar mass because you know how to do it. So these two are 96 plus 96. Aluminum is 27. And potassium is 40. Nope, it's 39. So the molar mass of this guy is 258 grams. So when you do this work, you get 0.00100 moles of potassium aluminum sulfate. So once again, we're figuring out how many moles of something we have. Now, if we have 2.16 grams of H2O and multiply by 1 mole of H2O per 18.02 grams of H2O, that's the molar mass of H2O. You get 0.121 mole of H2O. Now, what do you do with these two numbers? You do this. You take the 0.121 mole of H2O, divide it by the 0.001. I got one too many zeros in there. It should be 0.01 mole of potassium aluminum sulfate. And when we clean this up, we end up getting 12.1 mole of H2O per 1 mole of potassium aluminum sulfate. Now, this number here should be a whole number. So the question here is, do we think it's close enough to 12 to say, yeah, it's 12? And the answer is, yeah, it's close enough to 12 to call it 12. So that means that the formula here should be KAlSO42 dot 12H2O. And this would be called potassium aluminum sulfate dodecahydrate. And dodeca means 12. So for these hydrates, if you have one H2O, it's called monohydrate. Two H2Os would be called dihydrate, and so forth and so on. An interesting thing is this one. What would 1/2 H2O be called? And it's called hemihydrate. So why is it called hemihydrate? It's called hemihydrate because when you think of hemispheres, you got a northern hemisphere and a southern hemisphere. A hemisphere is half of a sphere. So what do you call half of an H2O? A hemihydrate. So that's how you figure out the formula of hydrates. And we're going to do a little bit of this tomorrow in lab. And here's a question for you. If you have 4.74 grams of the hydrate and you heat it, how do you know that all the H2O is gone? I mean, you can't see the H2O when it's there. You certainly can't see it when it's not there, but how do you know all the H2O is gone? Anyone have any ideas?
color change?
There's no color change in this one, but that's a great point. Greg, a lot of hydrates have a color change when they become dehydrated. And in fact, that's how people know whether or not you've dropped your cell phone in the toilet or the sink. You put a hydrate in there that turns I want to say red when it becomes hydrated, or maybe it's blue. So maybe red when it's dry and blue when it's wet. You send the phone back to them and say, hey, something's wrong with your phone. They open it up and they see the blue color and then they go, hey, well, you dropped it in the toilet. That's what's wrong with it. They can tell. But this particular hydrate doesn't change color. And not all hydrates change color, but it's a great point. Some hydrates change color. It's really cool looking. So how can we know it's all gone? So it would work, Greg, but it doesn't change color. Well, let me show you what you would do. Let's imagine we had a 30-gram test tube. Chances are you're not going to have a 30-gram test tube. And you have 4.74 grams of hydrate in there. And that weighs 34.74 grams total. Are you with me? When you heat it, let's say that the whole thing weighs 32.98 grams. And you want to know if all the water's gone. Well, you heat it again. And if you heat it again and it goes to 32.58 grams, what does it mean if the mass went down?
Not all the water's gone.
Not all the water's gone. And you heat it again and it goes to 32.58 grams. What does that mean?
You're done.
You're done. Or if it goes to 32.60 grams, you're done. It's close enough. Close enough. So this is what I call you heat to a constant mass. In other words, you heat it until the mass doesn't change. And you know all the water's gone. That's all you do. So what are we going to do to heat our compounds tomorrow? We're going to stick them in an oven at about 450 degrees for about an hour. And then you're going to weigh them. And then you're going to put them back in the oven. And the whole idea of putting it in a test tube and weighing them each time is that you don't have to fumble with pouring the solid out onto something and pouring it back in. You just weigh the whole test tube. And when the whole test tube and solid becomes the same, becomes a constant mass, you're done. And to know how much stuff you have in there, you just subtract the mass from the test tube. It's so neat and clean that you can't believe it. So that's how you do it. Does it sound cool or sound doable?
I got a quick question. Are we supposed to be getting supplies or am I supposed to have the test tubes?
You should have the test tubes. Did you get your box yet?
No.
Did you
Yes, I
did you
did.
send me your address?
Yep.
Huh. I will check into that, but I'm pretty all the boxes were sent out 2 weeks ago. Where do you live? Where do you live?
Address 143 Bay
Oh,
Street.
no. What town?
Eureka.
Eureka, huh? Okay, so you might want to go pick up your box. I will check the list I have. Well, let me check real quick. Do you have a moment?
I have plenty of time. You want to do this after class?
Well, we can do it right now. So class is over, everybody. I'm going to hang out with Greg and find out what's going on with his address and see if we got one out to him, okay?
Okay, bye. Have a good night.
Attending.
Good night.
And Greg,
Yes, sir.
I'm going to stop recording because we don't need to tell everybody your address.
I appreciate that.